Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone and welcome back to Physics with Beth and Beth. I'm Beth and today we are continuing our exploration of Unit 8 of AP Physics 1, which is on fluids. And so in this video we're going to be taking a deep dive into the idea of Archimedes' principle. But before we dive into all of this gross physics that I have on the board behind me, let's go back to something a little bit more familiar. Let's talk about some of the science that you guys probably did when you were in middle school or junior high. When I have a less dense thing and a more dense thing, the less dense thing floats, right? Oil floats on top of water because oil is less dense than water. If I mix a bunch of fluids together of different densities, they will eventually separate so that my most dense fluids are at the bottom and my least dense fluids are at the top. Less dense things float on top of more dense things. More dense things sink. So, for example, ice, water expands when it freezes, right? It goes from having a certain mass at a smaller volume to being the same mass in a bigger volume. So the density of ice is less than the density of water because it's the same mass divided by a bigger volume, right? So water on average has a density of about 1,000 kilograms per meter cubed. Well, ice has a density of 981 kilograms per cubic meter. So ice floats on top of water because it's less dense. Cork also floats on top of water. It has a density of about 250 kilograms per cubic meter, so corks float on top of water. A block of gold would sink if you dropped it into water because gold is more dense than water. Gold has a density of about 19,000 kilograms per cubic meter, so it sinks. None of that is too bad, right? This is probably stuff you've heard before, and even if you hadn't, less dense things float on top of more dense things. We can probably all be okay with that. So as we go through all of these gross words I'm about to read, I want you guys to hold that idea in your mind, okay? This is Archimedes' principle, that the upward buoyancy force on an object submerged in a fluid is equal to the weight of fluid that the object displaces. And then on your AP Physics equation sheet, you have this gross equation. But let's zero in on the first part of the sentence first. The upward buoyancy force on an object submerged in fluid. Now, in general everyday language, when we talk about buoyancy, we normally mean things floating in water, but buoyancy can refer to things floating in any liquid, whether that's water, another liquid, or even air. Buoyancy is things floating in any fluid, not just liquids necessarily. Now, the upward buoyancy force, let's talk about that. Actually, let's go back a little bit to something that you guys talked about way early on in this semester. I have a marker sitting in my hand, and it's not moving, even though the force of gravity is pulling downwards. Well, why is that? Well, there's another force that's acting against gravity pushing upwards, right? And we say that that's the normal force. The normal force is the force of my hand pushing up against this object that causes it to not be plummeting downwards towards the center of the earth, even though gravity is there. The buoyancy force is the same idea for objects that are floating in fluid. So if I have a little object and it's floating in water and the force of gravity is pulling downward, well, we know since it's not accelerating downwards, there has to be something canceling that out. And we call that something the buoyancy force. Woo. Now, it just so happens that the magnitude of the buoyancy force is equal to the weight of the fluid that the object displaces. So let's talk about how this equation allows us to calculate that. This equation is what's on your AP Physics equation sheet. And it is very confusing because it's just a bunch of letters. We have a density, we have a volume, we have gravity, but what density and what volume? So this density here is the density of our fluid, and this volume is the volume of our displaced fluid. So how is this allowing us to calculate the weight of the fluid the object displaces? Well, this equation looks a little bit different, but really what you're doing is something that you guys have been doing all year, which is F is equal to mg. Whenever we take the density of our fluid, well, density is equal to mass divided by volume, right? So we're taking the mass of our fluid divided by the volume, m over v, and multiplying it by another volume. V divided by V cancels out and we're left with M. So what this is calculating here in this little part of our equation is the mass of the fluid that our object is pushing aside. Then we're multiplying this by the acceleration of gravity, and this gives us overall the force of gravity on the fluid that our object is pushing away. So, wrapping all of that together, the upward buoyancy force on an object, the force that a liquid gives to keep an object from sinking down, is equal to the weight of the fluid that the object displaces, which we find by taking the density of our fluid times the volume of that displacement. Now, I could talk at you guys about physics all day. I really love talking about physics, but that's not super helpful. So let's actually start diving into a few examples of seeing how this works, because word salad is only helpful up until a point, right? So here I have a block of ice sitting in a beautifully and artistically drawn can of soda, or a cup of soda. So I have a block of ice that's 9/10 submerged, floating in a glass of soda. If the glass is taken to the moon, how much of the ice block would be submerged? Well, let's start out with a little free body diagram here. Y'all's favorite, I know. I'm sorry to say that they haven't gone away, and we will continue using them for as long as you're in physics. They just continue to be helpful. So, I have my block of ice that's floating in soda. Well, my block of ice has mass, so it has the force of gravity pulling downward, but it's floating, so I know something's opposing the force of gravity, something must be pointing upward. We call that the buoyancy force. Going back to Newton's second law, we know that the net force on our object is equal to its mass times our acceleration. Since our object is at rest, it's at equilibrium, we know the acceleration of our object is 0, so our net force is likewise 0. Anytime you have an object floating, the net force in the y direction is always going to be 0. So here we have that the net force on our object is equal to 0. The net force is the same as the sum of our two forces, so I have the buoyancy force pointing upward, and then I have the force of gravity pulling downward, so I subtracted it because it's going in the opposite direction. I can rearrange this little equation, and I end up getting that the force of gravity is equal in magnitude to the buoyancy force. Well, what is the force of gravity on my object? What's the force of gravity on my little ice cube? Well, it's just the mass of my ice cube times the acceleration of gravity, right? So let's take this guy over here. So we know the mass of our ice times the acceleration of gravity is equal to our buoyancy force, which we now know how to calculate because we just learned about it. So let's write a little equation for our buoyancy force. That's the density of our fluid times the volume of our displacement times the acceleration of gravity. Well, our volume of our displacement, that's what we're trying to figure out here, right? We're trying to see if the volume of our displacement, the amount of water that my ice cube pushes out of the way, and thus the amount of my ice cube that sinks, changes whenever I change the acceleration of gravity, whenever I take it to a different place, like the moon or Mars or Jupiter. Well here, this is our little equation here. We have the mass of my ice times the acceleration of gravity gives us, we know that that has to be equal to the density of our fluid times the volume of our fluid displaced divided by the acceleration of gravity. Well, I'm going to divide both sides by g and that cancels out. We know that the mass of my ice is equal to the density of my fluid times the volume that's displaced. Well, density isn't dependent on gravity. That's just mass divided by volume. That's not going to change when we go to the moon. The mass of my ice isn't going to change. The weight will, but the mass won't. I still have the same amount of ice. So the volume of our displacement isn't dependent on gravity. So our ice cube will float just as much in this water, or soda, or whatever it is that we're drinking, when we go to the moon as it does on Earth. Whew, that was a lot. Okay, let's go through a couple more example problems. Let's say I have a block of wood, or not a block of wood, a block of some material, like a chunk of metal or something, and it is sitting at the bottom of a tank of water. So once again, I have an artistically drawn drawing here. Now, a multiple choice question you might see on the AP Physics 1 exam would be something like, how does the density of the block compare to the density of the fluid that it's in? Well, we know that less dense things sink. wait, no, that's wrong. We know that more dense things sink, less dense things float on top of more dense things, right? So if we compare the density of our block to the density of the water, since it sunk, we know that the density of our block has to be more. So the density of our block, I'm going to say the density of our object has to be greater than the density of water. All right, that wasn't so bad. Now let's complicate things a little bit. Let's say that instead of having an object that sunk, I had one that floated. Like so. So it was half of my object stuck out above the water and half of it sunk. How would the density of my object here, my little block that's floating, compare to the density of the water? Is it equal? Is it less? Is it greater? Well, we know that less dense things float on top of more dense things. So we know it should be less dense, or else it wouldn't float, right? But how much less dense? Let me look over at my notes here real quick just so I can make sure I can show this correctly. So let's go back to our little free body diagram. We have our block. We know that the force of gravity is pulling down on our block, but we also know that the buoyancy force is opposing it, pushing upward, causing my block to float and not continue to sink downward. So I know that, well, the force of gravity on my block, well, that's just equal to the mass of my block times the acceleration of gravity, right? And then going back to that whole setup we had earlier, the net force on our block is 0. So the magnitude of my force of gravity is equal and opposite the magnitude of the force of the buoyancy force on my block. So I know that this is equal to the magnitude of my buoyancy force. So my buoyancy force is equal to the density of my fluid times the volume of my displaced fluid times the acceleration of gravity, applying Archimedes' principle here. I'm just going to go ahead and divide both sides by d. So now we know the mass of my block is equal to the density of my fluid times the volume of my displaced fluid. Well, let's rewrite this mass in terms of the density of my block, okay? Well, say I'm trying to write an expression for the mass of my block. Well, we know that mass divided by volume is just density, right? That's not how you spell block, there's a C in there. So if density is mass divided by volume, but then I multiply by volume again, like so, then I have volume divided by volume, which cancels out, and I'm left with just mass of my block. So I can write an expression for the mass of my block in terms of density if I just multiply it by volume to cancel out the secret v that's in the denominator here. So really all this is just the mass of my block. So I'm going to rewrite this here. So I have the density of my block times the volume of my block. Okay, now we have an expression that's letting us compare the density of my block to the volume of my block. I mean, the density and volume of my block to the density and volume of my displaced fluid. Well, if my block is halfway submerged in water, then the volume of my block is equal to twice the volume of the displaced fluid, right? Because half of it is underwater, half of it is above water. So my total volume is equal to twice of the water that I'm pushing aside. Okay, well now I have something on both sides of my equal sign. I'm just going to divide both sides by the volume of my displaced fluid. And now I know that 2 times the density of my block, I should run a subscript here so that's clear what I'm doing, is equal to the density of my fluid. So my block is half as dense as my fluid is. My block is half as dense as water. All right, guys, thank you so much for sticking with me through all of that. That is all we have on Archimedes' principle today. You guys are great, y'all are troopers, and happy physicsing.